1 milligram. A milli is 10 to the minus 3, and a gram is 10 to the minus 3 kgs. Okay, so the milli is 10 to the minus 3, and a gram is 10 to the minus 3 kgs. So that's the mass of the speck of paint. Its velocity is 4 into 10 to the 3 meters per second, and you got stopped in 10 to the minus 8 seconds. So that's the force you had to exert to stop that speck of paint. We'll bring this to the top. That becomes 10 to the 11 minus 6, 10 to the 5. So 0.4 divided by 6 into 10 to the power 5, and that's newtons. Roughly 6,700 newtons. Is that a problem? See, your weight is 600 newtons. That's 10 times your body weight. That's the force you have to apply. Okay, here's the problem. Yeah, that speck is tiny. See, if I apply a 10-pound force, this doesn't hurt, but this hurts. That little speck hitting the skin of your space station or the window the window would be okay, but it hits the skin of your space station, it can pop a hole. Yep.
Why was the final momentum zero?
You stopped it. If it bounces back, it causes more damage.
When you say the force exerted, do you mean the window exerting force on the paint chip to stop it?
Yep. And what does Mr. Newton say? The paint is exerting an equal and opposite force on the window. Okay, so a 2,000 kg railway freight car coasts at 4.4 meters per second underneath a grain terminal, which dumps grain directly down into the freight car. If the speed of the loaded freight car must not go below 3 meters per second, what is the maximum mass of the grain that it can accept? Okay, so now this is a real life problem. What they do is, so here's a grain car, and then you dump grain on as this passes. Yeah. Okay, so you have this setup where as this thing comes underneath, grain is dumped, and here's grain, and then this thing goes away at 3 meters per second. Why would you have a setup like this? You're processing everything fast, okay? You don't want things stopping and all that. It takes time, okay. Now, when it drops, the weight is in this direction, the normal force is like that. There's no force in this direction. So the momentum in this direction has to be conserved. Okay? So here's the initial mass. and here's the final mass. Okay. So initial mass, initial momentum is equal to final momentum. Initial mass times initial velocity equal to final mass times final velocity. So final mass is so the mass of grain that you're dumping is 933 kgs. Okay, so you increase the mass by 47%, essentially 50%. Yep.
So you're saying that as it passes by, it gets more grain, the velocity?
No, it was empty here. When it was underneath, you dump about 1,000 kg of grain, and it slowed down to 3 meters per second.
Where you're saying that the momentum stays the same?
Yeah, the momentum stays the same because when you're dumping, the weight acts this way, normal force act. All the forces are in the vertical direction. There's no force in the horizontal direction, which is what can change the momentum in that direction. You know? Yep.
So velocity is independent of momentum?
No, the mass, here's momentum. So if your mass increases, you will slow down. Well, so if you're driving real fast and your car engine can't do anything and you want to go faster, you throw out the passengers. Okay, so this says you're standing on a very slippery, icy surface and throw a 1 kg football horizontally at a speed of 6.7 meters per second. What is your velocity when you release the football? Assume you. Okay, so again, this is conservation of momentum. So you're holding on to a ball. Your initial momentum is 0. And you throw the ball, so you will recoil. Okay. And your final momentum should be 0 as well. So velocity of the person, velocity of the ball, mass of the ball. Okay. So final momentum is mass of person, velocity of person plus mass of ball, velocity of ball. Okay. So the football was 1 kg. The velocity of the ball was 6.7 meters per second. Mass of the person was 65 kgs. So the person recoils at a speed of 0.1 meters per second. The negative sign just telling you the direction in which you require. Okay. Mm-hmm. Okay, so here's a slightly complicated problem. Okay, so you launch a projectile and it will go on a parabolic trajectory. At the top of its trajectory, its y component of velocity is 0. So all it has is horizontal component. Okay? And then it explodes. So a projectile of mass 2 kg is fired in the air at an angle of 40 degrees to the horizon at a speed of 50 meters per second. So here's the initial speed launch angle. At the highest point in its flight, the projectile breaks into 3 pieces. So it's going horizontally, and it breaks into 3 pieces of mass 1 kg, 0.7, and 0.3 kgs. So here's the 0.3 kg that goes straight up. So just before exploding, what is the momentum? Its momentum is in the horizontal direction. So after it explodes, the 3 pieces must have a total momentum in the horizontal direction. Right? Okay. So this piece goes up, this piece goes straight down, this piece goes like that. So this momentum must cancel this momentum, and this momentum should equal this momentum. Okay, did you guys understand? Yeah.
Why is the momentum just horizontal?
At the top, your velocity is tangent to the trajectory. The velocity at any point is tangent to the trajectory. Okay. All right. So the 1 kg part falls straight down with an initial speed of 10 meters per second. This 0.7 kg moves in the original. Okay. Now, as an object is going in a parabolic trajectory, there is the y component of the velocity, there is the x component of the velocity. What happens to the x component of the velocity? Is there an acceleration in the x direction? No. So okay, so the x component of the velocity remains constant, so the x component of the velocity is just 50 cosine 40, okay? All right, so at the very top, so this was a 2 kg projectile. So the 2 kg projectile, so I'm just drawing this at the top, 2 kgs, and it's got a horizontal velocity of 3.3 meters per second. And this piece is, the forward traveling piece is 0.7 kgs, okay? So in this forward direction, this momentum should equal that momentum. Yeah. So 2 kgs times 38.3 meters per second should equal 0.7 kg times v. So it shoots off at 110 meters per second. Okay. So that's part A. Now part B says, how high from the breakup point does the 3 kg piece go before coming to rest? So it's shooting up at that speed, and how high will it rise? Okay. So the height it will rise. So you guys have seen this formula, H is V squared by 2G. Okay. So that's how high it'll rise. And that was 3.3 meters per second, 33 meters per second, square divided by 2 times 9.8 meters per second. Oh, this is 33 meters per second. Okay, 33 meters per second is about 75 miles an hour. And at that speed, it'll rise 50 meters. That's roughly the height of the tallest condominium on the beach. So if you throw a ball at 75 miles an hour, so if you get a major league pitcher to throw a ball straight up, that's how high the ball will go. Yep.
Is the height equation from, I believe, is it 1/2 mv squared equals mgy?
Yep.
And you solve
There,
for y.
yep. There you go. So that's conservation of energy. Kinetic energy got converted to potential energy.
So I was thinking, why can't you do mv equals mgy?
That's exactly
That's
what.
momentum, not.
Right. Correct. So, and anyway, so you guys understand? So this is a major league, well, it's not a major league. I don't know if I can throw at 75 miles an hour, but anybody a pitcher around here? No. All right. And then what is the last part? Where does the 0.7 kg piece land relative to where it was fired from? Okay, so this is slightly involved. Okay, so you shot it at 50 meters per second at an angle of 40 degrees. And what happened, it went in a parabolic trajectory. It was going at 38.3 meters per second. And then what happened, it exploded, and the piece that was going here suddenly is going at 109.4 meters per second. And this guy will also go on a parabolic trajectory, except that that trajectory is much wider. Okay, so that guy will go off the page. Okay, so what you want to calculate is D1 and then calculate D2. Did you guys understand that? Okay. We'll calculate the time of flight for this guy. Okay, let's say this guy takes 5 seconds to get there. So he's traveled 5 seconds. How long will this guy take to get down?
3 times as long?
5 seconds. His y motion is identical because he got to the top, he has 0 y component of the velocity, and then he's taking off horizontally, his y component of the velocity is 0. Okay? So here's a very interesting thing. So let's say we time this. This took 1 second to hit the ground. Yep. Now, what we'll do is instead we'll fire a bullet at 2 kilometers a second. How long will the bullet take to hit the ground? Same. Okay, same thing as that. All right, so we have to calculate these two distances. Okay, so we are calculating the x distance, x minus x naught equal to v naught x t plus 1/2 ax t square. This guy is 0. We'll call this 0. For we are calculating d1. And this is, so to get t, we'll calculate, so vy final equal to vy initial plus ayt. Okay, what we're calculating is the time it takes for it to get to the top. When it gets to the top, the y component of the velocity is 0. 0 equal to 50 sine 40 minus gt. So t is, you guys understanding this? Because at the top, your y component of the velocity is 0, okay? So 50 sine 40 divided by 9.8. So it took you 3.828 seconds to get there, and that's how long you will be in flight here. Okay. So this distance that you traveled is x is 50 cosine 40 times 3.28. Okay, so 125 meters, and D2 will be just this velocity times this time. So the total distance traveled is $60, 84. Okay. Half a kilometer. All right, let's do a few rocket problems and then we'll come back to the other problems. How much fuel would be needed for a 1,000 kg rocket? This is its mass with no fuel to take off from Earth and reach 1,000 kilometers per second in 30 seconds. The exhaust speed is 1,000. Everything is, okay, so V final minus V initial is V exhaust log. All right, what this tells you is this is the final speed of the rocket. There's the initial speed of the rocket, exhaust speeds. This is the initial mass of the rocket, so that's the mass of the empty rocket plus fuel. This is the final mass, acceleration due to gravity, and that's how long the engines were fired. Okay, so, and reach 1,000 kilometers per second. So 1,000 minus 0 equal to the exhaust speed is 1,000 log m initial, and final mass is 1,000 kg minus g times 30 seconds. Okay, those are all the numbers. So this works out to 1,000 equal to 1,000 log m initial 1,000 minus 9.8 into 30. $294. So 1,294 divided by that 1.294 equal to log m initial. And then you raise both to the power of 3, e to the power 1.294. So the initial mass of the rocket is 1,000 e to the power 1.294. Okay, so the mass of fuel is 2,647 kgs. Okay, so this was the initial mass of the rocket, and the final mass of the rocket is 1,000 kg. So this minus 1,000 kg gives you mass of the fuel. So you see, a rocket is mostly fuel. Okay. And now you see why your car cannot be called a rocket, because your car is mostly metal. Okay. So this problem says a rocket takes off from Earth and reaches a speed of 100 meters per second in 10 seconds. If the exhaust speed is 1,500 meters per second and the mass of the fuel burned is 100 kg, what was the initial mass of the rocket? Okay, so Again, VF minus V initial Okay, so what they give you now is the mass of the fuel burnt is 100 kg. Okay, so what they're giving you is mass final is mass initial minus 100. Okay, so that's how much fuel you burned. So reaches a speed of 100 minus 0, 1500 log mass initial minus 100 minus 9.8 into 10. Okay, so 198 divided by 1500 equal to log m initial. Okay, m initial is the only unknown, and you can solve for this. So it's 12, so B runs off like that, and C runs off at okay. So they want you to find the velocity of the rock. Okay. So this is a side view, this is a top view. Okay. Okay, what you want is the final momentum to be equal to initial momentum equal to 0. So mass of the rock times velocity of the rock plus mass of the deer times velocity. So masses are the same, so I pulled out okay, so mass of the rock times its velocity should equal mass of the deer A times its velocity. So these momenta should add up to 0. Mass of the rock is 200 kgs, velocity of the rock plus 70 times, okay, let me do this. Okay. Now we just need to add these velocities. We need to add these velocities, A, B, C. So that's 15 minus 12 is 3. 3 plus 1 is 4.2. And then this is 5, 13. 13 minus 18 is minus 5. So velocity of the rock Okay, so the velocity of the rock is in the third quadrant actually. Okay. All right, so here's an interesting problem. A cube of side A, so this side is A. Oh no, a cube of side A is cut out of another cube of side B. So this side is B, as shown in the figure. Find the location of the center of mass of the structure. Okay, so think of the missing part as a negative mass overlapping the positive. Okay, so if this was there, if this whole cube was there, then the center of mass would be at the geometric center, which would be B by 2, B by 2, B by 2. And now that you've removed this piece, the center of mass of this guy goes further out. Did you guys understand that? All right, so you want to find the center of mass of that. Okay, so what we'll do is we'll do the following. Let's say we'll assume the center of mass of this to be X, Y, Z. The center of mass of this guy to be X, Y, Z. So if you had this guy and this piece, then we know the center of mass of those two pieces. That would be B by 2, B by 2, and B by 2. Okay? All right, so we'll call this mass M1 and this mass M2. Remember the formula for the center of mass? X center of mass is Mi, each piece, times the center of mass of that piece divided by the total mass. Okay, so what we're doing is we're putting this mass back. If you put this mass back and take this mass, the center of mass of these two pieces will be B by 2. Did you guys understand that? B by 2 is equal to M1. What is the center of mass of this guy? X coordinate, A by 2. Plus M2 times the center of mass of this guy is X coordinate is X, which is what we want to try and find. And then the total mass, which is M1 plus M2. I'll call it M. Okay, what is M1? M1 is the fractional volume, A cube by B cube times M. Okay, who can tell me M2? m is the mass of the whole thing. To find this mass, you just had to get the fractional volume, a cubed divided by b cubed times m. To get the mass of this guy, you had to get its volume. Its volume is b cubed minus a cubed divided by b cubed times m. Right? So now we'll substitute this over there. So so b by 2 is equal to a cubed b cubed times m plus m2 is b cubed minus a cubed by b cubed times m x divided by m. And so you see the m cancels. And so b by 2 is a cubed by b cubed plus b cubed minus a cubed by b cubed times x. What are we solving for? X. Okay. So x is b over 2 minus a cubed by b cubed divided by b cubed minus a cubed over b cubed. X is so b cubed times b over 2 minus a cubed over b cubed. Oh, I missed out a over 2 here. There's, so m1 is that, and then there's an a over 2. So b cubed times b over 2 minus a over 2 a cubed by b cubed. All right, pretty ugly looking thing, but let's, okay, so 1/2 b to the power 4 minus a to the power 4. Okay, now it's looking good. So x is that. One half b4 minus a4. All right, let's see if it has the right limits. If a were to go to 0, x should become b by 2, right? The center of mass of this guy, the x-coordinate should be b by 2. If a were to go to 0, this would be 0. b4 divided by b cubed x will become b by 2. So it's the right value. Okay. If a is not 0, this should be, x should be greater than b by 2. Okay, so let's see if is 1/2 b to the power 4 minus a to the power 4 divided by b cube minus a cube, is it greater than b by 2? Okay, it should be greater than b by 2. So the halves cancel, b to the power 4 minus a to the power 4 equal to b cube minus a cube. Is it greater than b? Okay, so b to the power 4, a to the power 4, is it greater than b to the power 4 minus a cube b? Is this true? Is this true? Okay, so b is bigger than a. Here's b to the power 4. And b to the power 4, you're subtracting a to the power 4. Here's a cube, and b is bigger than a, so this number is bigger than this number. So you're subtracting a bigger number than that, so this number is smaller than that number. Okay, so this is true. Okay. All right, you found x. This is the center of mass coordinate for this piece. What are the y and z coordinates? Very good. Very good. Okay, so x, y, z are equal to, and this is a very symmetric expression. Now, okay. Okay, I'll quickly set up this. This is an integral, so I'll quickly do this guy. We have a few minutes to do this. Find the center of mass of a thin wire of mass m and length L bent into a semicircular shape. So, okay. Let the origin be at the center. So there's the origin. Okay. You want to find the center of mass of this. Okay, so if this was a full circle, then the center of mass would be right there. The center of mass would be x equal to 0, y equal to 0. But this other half is not there, so it's only this. But anyway, the center of mass has got to be somewhere on the y-axis. So the x center of mass is 0. What is the y center of mass is the question. Okay? And the center of mass is somewhere there. Yep. And we got to find that. All right. You guys saw the formula for a continuous distribution. Y center of mass is dm y dm divided by the total mass, where dm is this mass and there is y. Okay, so that's the expression. All right, what we'll do is this is theta, this is d theta. Okay, so the y center of mass, dm. Okay, what is dm? Dm is the mass of this piece. Okay, and that piece is so what is this angle? Oops, what is this angle? This angle is pi. So d theta divided by pi, that's a fractional angle, times mass m. Okay. The mass of the whole thing is m. So this is the fractional angle. That's the fractional mass. That's that. And then y is let's say r is the radius. Pi r is L. So r is pi over L. Okay. Y is r sine theta. Sine theta is y over r. So okay. Okay. Sine theta is y over r. So y is r sine theta. Okay. And we're going to put all of that in here. So y center of mass is y is r sine theta. Dm is d theta pi times m. And the mass of the whole thing is m. And what is r over pi is 1 over L. Oh, I'll keep it r over pi. Sine theta d theta. Okay. So, and theta goes from 0 to pi. Minus, so I'll pull out the minus r over pi. Cosine cosine pi is minus 1 minus of cosine 0, 1. So this is equal to 2 over pi times r. All right, so what we found is y center of mass is 2 over pi times r. Let's see, does that make sense? Here is the semicircle. There is r. There's r. 2 over pi is roughly 2/3. So the center of mass is somewhere there. Y center of mass is somewhere there. And that makes sense. Okay. All right.